Welcome to This Explainer. Today, we're cracking open the ultimate explorer's toolkit for navigating the absolutely fascinating world of secondary science. So if you are ready to look a little closer, think a bit more carefully, and truly make sense of the nature and technology all around us, well, you're in exactly the right place. Let's get right into it.
Okay, we need to start with a major mindset shift here. Because true science, it's way more than just memorizing a giant list of equations or dusting off a collection of old facts. It's actually a super dynamic, human activity driven by pure curiosity. Fundamentally, it's a toolkit for surviving and understanding our incredibly complex, often messy world. Honestly, it's not just about what we know, it's about how we know it.
Think about a magnifying glass for a second. It perfectly captures our first core concept, the absolute need to observe the world really carefully. We have to pay attention to the little things that usually just slip right by us. It's all about spotting those hidden, underlying patterns buried in the everyday noise of our lives.
But, observation alone just isn't gonna cut it. Just like an explorer needs a compass, true exploration needs serious direction. We can't just wander around aimlessly. We have to choose the right models, ask really purposeful questions, and, this is crucial, we have to understand the boundaries of where our ideas actually apply.
Tool 1. Making simple models. Now this might actually surprise you, but our first real tool relies entirely on the art of deliberately ignoring things. Seriously, take a classic question. If you hit a cricket ball for a 6, will it cross the boundary without hitting the ground? If you want to answer that, you literally cannot calculate every single detail of the universe at once. The natural world is just way too complex to study in full HD detail. So, here's the trick. To build a useful model, we have to boldly toss out the useless details. Think about it. The brand of the cricket bat, the color of the ball, exactly how much grass is on the field. None of that actually matters for figuring out the ball's trajectory. We only keep the vital stats, like the mass of the ball, its speed, and its direction. And to be clear, these choices aren't lazy mistakes. They are highly strategic simplifications.
And hey, this isn't just for sports. The physicist Meghnad Saha used this exact same tool to unlock the cosmos. When he was studying starlight, he didn't try to mathematically model every single atom or crazy complex chemical reaction. He just completely ignored them. He simply treated the star's matter as a hot gas. And that one brilliant, simple model is exactly what allowed him to discover how a star's color is directly linked to its temperature. Pretty amazing, right?
Tool 2. The shared scientific language.
When scientists throw around words like force or work, they aren't just being poetic, they are communicating with pinpoint accuracy. And this shared, precise language, it can literally be a matter of life and death, especially when it comes to standard units. Take this terrifying real-world disaster. A passenger plane needed exactly 22,300 kilograms of fuel, but the ground crew messed up and calculated the fuel density in pounds per liter instead of kilograms per liter. And as you can probably guess, pounds and kilograms are very different things.
That one little mix-up left the aircraft a whopping 15,000 liters short of fuel while they were mid-air. Now, thankfully, the pilots managed a miraculous emergency glide and everyone was okay. But man, this perfectly highlights why using standard global scientific units isn't just some boring homework exercise. It is absolutely critical for our safety, for fairness in global trade, and for making sure we can actually compare scientific results all over the world.
Oh, and fun fact for you, the universal math and symbols we use actually have some really cool backstories. Like the speed of light, we use the letter C for it because it comes from the Latin word celeritas, which means speed. It's a great reminder that math and science isn't supposed to be this awful hurdle of equations you have to memorize. It's actually a rich, historical language that helps us reason clearly about how different things in our universe connect.
Tool 3. Frameworks and predictions.
Okay, one of the absolute coolest things about science is how it uses established frameworks to literally predict the future, way before we even run an experiment. Now, you've probably heard some of these terms thrown around. Take a law. In science, a law specifically describes a regular, predictable pattern we observe in nature. For instance, Newton's laws of motion are what mathematically explain that sudden, annoying physical jerk you feel when you're on a bus and the driver slams on the brakes. Then we have a theory. And let's clear this up right now. A scientific theory is definitely not just a random guess. That's a massive misconception. A scientific theory is a rigorously tested explanation of why those patterns occur, backed by mountains of evidence, like the atomic theory, which explains exactly how molecules are formed.
And the best part? Theories are completely open to being improved when new evidence rolls in. That flexibility is exactly why science is so reliable.
And finally, we have a principle. This is a broad idea that helps us make sense of very specific situations. A classic example would be applying the principle of the conservation of energy to figure out the sheer physics of dragging yourself up a huge flight of stairs.
So why does all this terminology matter to you? Well, because we can actually use these precise frameworks to test the wild viral claims that pop up on social media every single day. Take that super popular myth that food instantly goes bad if you eat it during a solar eclipse. If we just apply a basic scientific framework, we have to ask, okay, what physical change is actually happening here? And we quickly realize an eclipse is just a physical shadow. That's it. There is no magical chemistry happening that's going to ruin your dinner. Boom. Myth totally busted by basic scientific questioning.
Tool 4, the power of estimation.
Now, this next tool might completely change how you think about math and science. We're talking about the awesome power of rough estimation. Let's try it together right now. If I asked you exactly how many liters of air you breathe in a single day, you'd probably panic and go hunting for a textbook. But check out how easy this is if we just estimate. Step 1. We can guess we take about 15 breaths a minute while resting. Step 2. Multiply that by the 1,440 minutes in a day. Step 3, to get the volume, just picture a standard 2-liter party balloon. It takes roughly 4 breaths to fill one up, so each breath is about half a liter.
And there you have it. Just by using that quick, intuitive math, we can confidently estimate that you breathe in about 10,000 liters of air every single day. No crazy complex equations required whatsoever. This kind of back-of-the-envelope estimation is so powerful because it instantly tells us if an answer is totally impossible or actually pretty reasonable.
Connecting the branches.
Now, in school, we tend to chop science up into neat little boxes. Physics, chemistry, biology, earth science. But out in the natural world, those boundaries do not exist at all. Think about something as everyday as a surgical mask. To truly understand how it blocks a virus, you need physics for the electrostatic attraction of the particles. You need chemistry to understand those polymer fibers. You need biology to know the size and behavior of the virus. And you absolutely need mathematics to model the airflow. Real-world problems are messy, and solving them requires all these disciplines working seamlessly together as one.
Which brings us to the end of our explainer today. But really, it's just the beginning of your journey. Even if you have zero plans to become a professional scientist, thinking this way is an absolute superpower. So I'll leave you with this one crucial question. How are you going to use this newfound scientific toolkit, your ability to build simple models, demand precise language, use testable frameworks, and estimate logically to evaluate the wild technology and viral information you're going to bump into tomorrow? Keep that magnifying glass handy, always check your compass, and happy exploring.